Welcome to Kings Mountain, North Carolina, home to one of 3 BALDOR plants that build above NEMA AC motors. It's appropriate to begin the tour with incoming materials inspection. Here, materials are checked to make sure they comply with BALDOR's rigid design specifications. Selection of magnet wire samples takes into consideration the different suppliers, wire sizes, and manufacturing dates. Testing includes 6 different procedures that involve elongation, bending, and baking the magnet wire. These tests help to nurture both supplier excellence and product quality. High voltage testing is done to be sure the windings will withstand voltage surges. All test data is downloaded into the plant's Infinity SPC database to establish conformance and long-term process controls. Copper rotor bar concentricity is critical to eliminating the sources of motor vibration. Here, measurements gauge concentricity from top to bottom and side to side throughout the length of the bar. Lamination steel used in the stator plays a key role in maintaining consistent and efficient electrical performance. The Epstein and Franklin tests shown here measure the chemical, physical, and insulating properties of our lamination steel. Shaft machining begins with a steel blank. Then all the surfaces and shoulders are turned in a single process. Next, we mill the keyway and drill the centering holes at the end of the shaft. Because low vibration and bearing life are so important to customers with critical service applications, we finish grind the entire length of the shaft, including the rotor core, where a perfect fit with the shaft is essential to keeping motor vibration in check. Making laminations begins with punching the stator and rotor blanks. Precise stator lamination geometry is the key to optimizing heat transfer inside the motor. With slot notching, we also get a clean edge in order to avoid damage to the magnet wire during the winding process. By notching rotor laminations, we are able to maintain extremely tight tolerances. Notching also makes it easier and faster to adjust slot configurations and facilitate rapid design changes. All finished laminations go through a quality check of the dimensional consistency between laminations. Heated laminations cool and shrink on the arbor. Then the stack is compressed from top to bottom. In the die caster, molten aluminum enters the core from the bottom. This forces air out through the top and prevents rotor porosity. As the core is removed from the arbor, notice the vent holes at the top. This honing process yields a perfectly sized and round bore. We typically hone the bore for motors and applications where low vibration is required. After honing, the rotor core is heated and expanded before we insert the shaft. For ultra-precision balanced motors, gradually cooling the rotors relieves stresses and reduces vibration. The assembled rotor and shaft is now balanced. Our loose-fit rotor bars are not restricted and are able to maintain their geometry as they heat up. Next, bars are brazed to the end rings with an exclusive process that prevents warpage and bar breakage. The turning lathe shown here trues up the end rings and brings them to the proper size. Prior to vibration testing, the assembly is given a protective coating. This slow roll procedure checks mechanical and electrical shaft runout. Just like the rotor cores, precision and concentricity are critical to building high-quality stator cores. To ensure a tight fit between laminations, the core is compressed and welded straps are applied. Applying Lean and Six Sigma to our coil cell reduced cycle time from 21 days to 7.5 hours. All the key processes in this cell, such as winding, shaping, and insulating, are computer controlled. This coil winder, for example, maintains constant tension on the wire as the coil diameter builds. With this kind of precision, we can be confident that all completed coils are exactly alike. Robotically taping the magnet wire periphery puts repeatable precision where you need it most. During taping, insulation tension and the critical insulation overlaps are tightly held to exacting specifications. Standard practice for making form-wound coils often involves a lot of arm wrestling and hammering that yields dissimilar parts. This is no longer an issue with our computer-controlled capabilities. Here, the engineer indirectly controls every step of this spreading and shaping process. Slot lining and insulation paper make it easier to insert the coils without damaging the coil tape. Here you get the feel for what it takes to get the coils properly located. Our loop connection for sealed insulation systems will seal off the lead connections, making it impossible for moisture to reach this important junction. Before going to varnish, the stator gets a surge test to ensure coil integrity. We also high pot the windings to ground as a final check before varnish. Vacuum pressure impregnation uses vacuum to eliminate all air voids in the coils and varnish. Then, pressure is applied to force resin into the coil tape. Stator quality is the foundation of a great motor. So we horizontally bake and rotate the stator to improve varnish distribution, penetration, and utilization. Again, stator quality is a dominant concern. So we take the extreme measure of immersion testing all of our EnduraSeal stators. Here you get a good look at the motor frame being lowered onto the stator core. Moving further along the assembly process, the rotor, shaft, stator, and frame all come together. Since sleeve bearing surfaces must be perfectly round, they are polished before assembly. Sleeve bearing assembly begins with the oil rings. Once the edges of the bearing hub are trimmed, the bearing halves are mounted. Finally, the top half of the hub is added to the assembly. Note the bearings shown here are insulated. Here, the RTD probes are being positioned. Three-dimensional coordinate measurements are a critical element of our quality plan. For example, all of our sleeve bearings go through the CMM machine. Here, key components such as the bore, rabbet fits, and seals are measured against design tolerances. The anti-friction bearing you see here is being prepped for assembly. Here, the sleeve bearing assembly is mounted to the motor frame. Next, the anti-friction bearing is mounted. Followed by the fan. And the fan cover. Kings Mountain can do full load dyne testing up to 4,500 horsepower and 7,200 volts. In order to isolate this motor during vibration testing, note that it is bolted to a seismic mass. During the paint process, quality is still the priority because we know paint durability and appearance are important to our customers. Now, as we take a look at a few products, you will see some of the craftsmanship put into every motor built in this plant. This is a TEFC motor with a low-noise fan cover. This TEFC motor has sleeve bearings and an auxiliary blower. This 9500 frame weather protected motor is a typical critical service design for the petroleum industry. This shows a customer's half coupling and several accessories. Cooling air enters through these top vents and exhausts from the bottom. Lastly, a BALDOR water-cooled motor and gear. We hope this video helps you appreciate our capabilities and our passion for building great motors. BALDOR, the industrial choice.